let's see if we can pick up where we left off in part 1. We're going to start down here with solutions. Solutions should still be fresh in everyone's mind because we did take a solutions test not too long ago. Actually, we were already in digital learning when we took our solutions test. So looking at number 13, it says, what is the formula for finding molarity? The formula for finding molarity, remember, would be moles of solute over liters of solution. So moles of solute divided by liters of solution is our formula for finding molarity. Well, then let's find the molarity. Well, if molarity is equal to moles of solute over liters of solution, then what is the molarity if we have 500 milliliters of solution that contains 425 grams of cobalt bromide? Well, what do I have here? I have 500 milliliters, that's not liters, but that's easy enough to fix. And then I've got 425 grams of cobalt bromide. Well, if I have 425 grams of cobalt chloride, I'm going to have to change that into moles before I can get my molarity. So 425 grams of cobalt bromide. Got to change this into moles. Okay, 1 mole of cobalt bromide, and now I've got to get the molar mass of cobalt bromide, and it just so happens that I have that right here. It is 298.63 grams. So 425 grams of cobalt bromide, 298.63 grams for each mole, and that's going to give me 1.42 moles of cobalt bromide. Well, to get my molarity, now I've got 1.42 moles of cobalt bromide in every 500 milliliters. Well, 500 milliliters is 0.5 liters. So now all I have to do is divide. 1.42 divide by 0.5. And when I do that, I get 2.85 molar. So if I have 500 milliliters of solution and it contains 425 grams of cobalt bromide, that's a 2.85 molar solution. All right, so let's look down at number 15. How many moles of sodium chloride will you need to make 550 milliliters of 1.5 molar solution? Well, this is going to be a proportion. Well, and here's my first fraction, the proportion right there, 1.5 molar. Doesn't 1.5 molar mean that I have 1.5 moles of sodium chloride in every 1 liter of solution? I believe that it does. That's got to be equal to, well, which do I have? Do I have moles or do I have liters for the rest of this? Well, 550 milliliters. So I really do have my liters because this would be 0.550 liters. To get milliliters to liters, divide by 1,000. So what I don't know then are how many moles I've got. Well, we all know that to solve a proportion, I have to do cross multiplication. So what that's going to mean, 1.5 moles times 0.550 liters is equal to 1 times x. So when I do that, what I end up with is 0.825 moles of sodium chloride are necessary. So that would be, again, 1.5 times 0.550 divided by 1 is equal to how many moles? And that would be 0.825 moles of sodium chloride. Or thinking about significant figures, I've got 2 sig figs here, so really 0.83 moles if we want to use our significant figures, which we should. So let's move along then to our next page, which starts out with a solubility curve. So let's think about what's going on this solubility curve. I know it's a later question, but let's go ahead and put it in place here just so that we know what's going on. On my y-axis of the solubility curve, it's labeled grams of solute per 100 grams of water. And then what was this down here? 10, 20, 30. This, remember, was our temperature in degrees Celsius. Temperature in degrees Celsius. Well, that's this first question right here. The x-axis isn't labeled. What variable goes on the x-axis in solubility graphs? And that would be temperature in degrees Celsius. So let's take a look up here at this upper question. Sometimes you can't just look at the graph. Most of the times we can simply look at the graph. If we see where the temperature is, we come straight up and we see how many grams of solute we can put into that, how much solute we can have dissolved into that solution. But there are some times when we can't, okay? Sometimes we're going to have to use a proportion in order to solve this. And remember, the proportion is always set up grams of solute over 100 grams of water is equal to how many grams of solute. I'm going to put a 1 here and a 2 here. Grams 2 of solute over the new grams of water. So grams 2 of water. So it's always going to be grams of solute over grams of water, equal to grams of solute over grams of water, and the first grams of water is always going to be 100. Now, what are the times that you're going to use these proportions? There are 2 things that have to be the case in order to use a proportion to solve a solubility curve problem. 1, the temperature must stay the same. So in other words, the temperature must be constant. Temperature has to be constant. And not only does the temperature have to stay the same, but what you're actually changing here is the amount of water. So the amount of water changes. And of course, obviously, you have to have the same solute. But it goes without saying here. So the water is changing and the temperature stays the same. That's going to be your clue that you have to work the problem like this. Grams of solute over 100 grams of water equals grams of solute over grams of water. So let's see if we can solve a few of these. Okay. Starting with an easy one. How much sodium nitrate dissolves in 100 grams of water at 45 degrees? Well, first thing I'm going to do is I'm going to come out on my x-axis to 45 degrees. So here it's going to be 40, here's 40, here's 50, so 45 is halfway in between. I'm going to come straight up to my sodium nitrate line. So straight up to the sodium nitrate line, which is all the way up here. So right there. So all the way up here to the sodium nitrate line, that's going to give me that point right there. So if I come straight across, that tells me that I can put 110 grams of sodium nitrate in 100 grams of water at 45 degrees Celsius. C. What type of solution has 40 grams of potassium chloride in 100 grams of water at 90 degrees Celsius? Well, it's in 100 grams, so I don't have to worry about that because the whole chart is that way. So let's take a look at potassium chloride at 90 degrees Celsius and see what number we have there. Well, 90 degrees Celsius, out to 90 degrees Celsius, and then up to my potassium chloride line. Well, here's my potassium chloride line. So what is this number right here? At 90 degrees Celsius, I can fit 50 degrees. I can fit, 50 grams. Well, if I can put 50 grams in there, but I only have 40 grams, well, here's 40 right here. That's below the line, so this would have to be an unsaturated solution. Look at D. What typically happens to the solubility of solids as the temperature increases? Well, if we take a look, here's a solid, here's a solid, there's a solid, there's a solid. Okay, when the temperature increases, the solubility of a solid also increases. What typically happens to the solubility of a gas as the temperature increases? Well, the solubility of a gas, when you increase the temperature, decreases. So, looking at that then, what two solutes on this graph are behaving like gases? Well, that one goes up, that one goes up, this one goes up, and this one goes up, and then so does this one. So that only leaves this one and this one that are going down. So that's going to be ytterbium sulfate and cesium sulfate. So the ytterbium sulfate and cesium sulfate, those are the two that are behaving like gases. As the temperature increases, they are actually losing solubility. All right, so for G, let's take a look at G. G says, if a saturated solution of potassium chloride dissolved at 100 degrees, so 100 grams of water at 90 degrees is cooled to 60 degrees, how much will precipitate out? Well, first, let's look and see what are the things that I need to know. My x-axis is 90 degrees to start with, and potassium chloride is my solute. So first, let's go out to 90 degrees and go up to potassium chloride. Well, I've already been there. I've already been to that spot. Potassium chloride, it's 100 grams of water, 90 degrees Celsius. So we go to 90 degrees Celsius and up to potassium chloride. That looks like about 55. So it's just below the 60 line. So 55, I can put 55 grams in there at 90 degrees. If I cool it to 60, how much will precipitate out? Well, at 60 degrees, look at my potassium chloride line. Here's 60 degrees at my potassium chloride line. So that looks about 45. Well, if I put 45, if it has 45 in there at 90 degrees, or it has 55 at 90 degrees, and I cool it down to 60 degrees where I can only put 45, then that means that 55 minus 45 is 10 grams. So 10 grams had to drop out of solution. How much sodium nitrate will dissolve in 450 grams of water at 20 degrees Celsius? All right, this may be one of our proportion problems here. 20 degrees Celsius, so my temperature is not changing, but I want to know how much is in 450 grams of water, which means that my water volume or water mass is changing. So let's see what we can do here. I know I'm working with sodium nitrate, 20 degrees Celsius. So here's 20 degrees Celsius. Let's go up to the sodium nitrate line. 20 degrees Celsius up to sodium nitrate. And that looks to me at about 89 grams. So at 20 degrees Celsius, I can put 89 grams of sodium nitrate in 100 grams of water. But I want to know how many grams of sodium nitrate I can actually put in here if I have 450 grams of water. So if I can put 89 grams in 100 grams of water at 20 degrees Celsius, how many grams of sodium nitrate can I put if I have 450 grams of water? I have a proportion here, which means that I can solve this by cross multiplication. 89 times 450 is equal to 100 times x. Well, 89 times 450 is 40,050, and then divide by 100, and so what I end up with then is 400.5 grams. But if we take into consideration our significant figures, 3 here, so that's going to end up being about 401 grams. So we should be able to put 401 grams of sodium nitrate into 450 grams of water at 20 degrees Celsius. All right, looking at the last one on this page. 65 grams of barium hydroxide are dissolved in 100 grams of water. How much additional barium hydroxide will dissolve? Well, so let's first start. I've got barium hydroxide. It's in 100 grams of water, so there's no proportion necessary at 80 degrees. So let's go up here to the chart. 80 degrees. Let's go up to the barium hydroxide line. 80 degrees and all the way up to barium hydroxide. So right there. So that would be, I can put 100 grams of barium hydroxide in there, but I've only put 65 grams. So 100 grams minus 65 grams is going to give me 35 grams. So how much additional barium hydroxide would dissolve? 35 grams. So there are some sample solution problems right there. Okay, so this next segment here says that I'm going to do acids and bases. Well, we just did acids and bases, didn't we? So this should be easy peasy. So let's move it on over to the acids and bases. We can zip through this really quickly. Okay. How did Arrhenius define acids and bases? Well, Arrhenius, remember, hopefully you remember because you are taking, this test is Tuesday, April the 14th. Arrhenius classified acids as having hydrogen ions and bases as having hydroxide ions. On a pH scale, acids have a value that is less than 7. Bases have a pH value that is greater than 7. Acid-base indicators. Okay, for acid-base indicators, remember we have pH paper. You have litmus paper, both red and blue. We have universal indicator, which is a liquid that does exactly what pH paper does. And also phenolphthalein. So those are all our acid-base indicators, things that will indicate whether or not a substance is an acid or a base. So let's take a look at what each of these indicators will do in an acid or a base. Red litmus paper in an acid will stay red. blue litmus paper in an acid will turn red. Phenolphthalein in acid will remain clear. Red litmus paper in a base will turn blue. Blue litmus paper in a base will stay blue. Phenolphthalein in a base will turn pink. Red litmus paper in a neutral solution will stay red. Blue litmus paper in a neutral solution will stay blue. And phenolphthalein in a neutral solution will stay clear. So looking at A through F, we're going to be determining whether or not a substance is a strong acid, strong base, or weak base. Now remember how it is that we determine that. In A, the substance dissociates completely. Well, if it dissociates completely, that is our clue that this substance is a strong something. So I'm going to come all the way over here already and write strong, because I know it's going to be strong. And it turns blue litmus paper red. Well, we just wrote that down. What turns blue litmus paper red? Something that's acidic. So this would be a strong acid. B, something that partially dissociates. Well, if it partially dissociates, that's my clue word right here, partially. That means this is going to be a weak something. It stays clear in phenolphthalein. Well, what is clear in phenolphthalein? Both something that's acid and something that's neutral. We're not talking about neutral stuff here. So this is going to be a weak acid. Dissociates completely. So now we're back to this dissociates completely. So this is going to be a strong something. And it has hydroxide ions. Well, what has hydroxide ions? Arrhenius tells us that bases have hydroxide ions. So this is going to be a strong base. It dimly lights up the conductivity apparatus. Well, dimly lighting up the conductivity apparatus means that it is dissociating only partly because it's only partially ionized. So this is going to be a weak something. And it turns pink in phenolphthalein. Well, pink in phenolphthalein tells me that it's a base. It brightly lights up the conductivity apparatus. Well, if it brightly lights up the conductivity apparatus, that means that it's 100% ionized, which means it has dissociated 100%, which means that it's a strong something, and it has a pH of 2.1. Well, a pH of 2.1 means that it's acidic, so this would be a strong acid. And then finally, it dissociates completely, which means it's strong. And it dissociates into hydrogen ions. Well, Arrhenius defines acids as having hydrogen ions, so this also would finish this section out with a strong acid. pH. Let's take a look at pH. If the concentration of hydrogen ions is equal to hydroxide, that has a pH of 7, and we call that a neutral substance. If hydrogen ions are greater than hydroxide, remember, what is it that has hydrogen ions? That would be an acid. So that's going to have a pH that is below 7, and it is an acid. If the hydrogen ions is less than the amount of hydroxide ions, then it has a pH that's greater than 7, and we say that this is a base. We could also call that alkali. All right, Moving on down. Decide whether the unknown A and unknown B, and then of course there's some on the next page. Decide whether that is an acid, or is it alkaline, or is it neutral. pH of 6, well, 6 is less than 7, therefore this would be an acid. Unknown B, 7.6, well, 7.6 is greater than 7, so this would be a base or alkaline. Finishing out this chart, unknown C has a pH of 10. Well, 10 is greater than 7, so this also is alkaline, which we also refer to as being a base. Unknown D, 4.1. 4.1 is less than 7, so that would be an acid. And unknown E has a pH of 7, which is, of course, neutral. All right, conjugate acids and bases. Well, the only person who talked to us about conjugate acids and bases was Bronsted-Lowry. The Bronsted-Lowry, the only theory that talks to us about conjugate acids and bases is Bronsted-Lowry. So let's see what we have. We need to identify things as being acids, bases, conjugate acids, and conjugate bases. Well, in order for us to do that, we just have to remind ourselves, and the light is encroaching more and more on us here. All right, now that we've taken care of our light problem, let's see if we can move on. Well, remember in Bronsted-Lowry, I'm just going to write this up here for us so that we remember, in Bronsted-Lowry, an acid will donate hydrogen ions, whereas a base will accept hydrogen ions. So acids will donate hydrogen ions, bases will accept a hydrogen ion. So let's look down here. Well, I've got H2SO3, sulfurous acid, and look on the other side. Well, that's not it, but here we are with SO3 again. So this has become this. Did it donate or accept a hydrogen? Well, I've got H2 here and only H1 here. Well, if I have one hydrogen on one side and one hydrogen on the other, going from here to here, this would be a donated, so that is an acid. Well, acids become conjugate bases. H2O becomes H3O. So 2 H's here, 3 on this side. So it accepted a hydrogen ion. Since it accepted a hydrogen ion, that would be my base, which would make this H3O, which is hydronium, on this side, our conjugate acid. Look at letter B. In letter B, I have NH3, and over here it's NH4. That means it accepted a hydrogen ion from the left to the right. So if it accepted, that would be our base, which makes this the conjugate acid. Notice again, just like when we reviewed for acids and bases, acid and base are on the reactant side. Conjugate acids and bases are only on the product side. H2O becomes OH, which means that we lost hydrogen ions. Okay, so it donated hydrogen ions. It donated a hydrogen ion, which makes it an acid. If this is an acid, it becomes a conjugate base. Then finally, H2O to OH. Well, it has one more hydrogen on the left than the right, so it donated a hydrogen, which makes it an acid, and which means this side is our conjugate base. Cn becomes HCN, so it accepted a hydrogen ion, so that means that's a base, and it becomes our conjugate acid. Now, to finish things up, let's deal with neutralization. What are the reactants in a neutralization reaction? Well, if we're talking about neutralization, we're talking about an acid and a base reacting with each other. What is produced in a neutralization reaction? A salt, an ionic salt, and water. What type of a reaction is neutralization? This would be a double displacement or double replacement reaction. All right, now let's finish things out by writing and balancing chemical equations for these neutralization reactions. Let's see if we can write down what these acids are. Hydrofluoric acid. Well, hydrofluoric acid, you see the hydro in front, so it is a binary acid, fluoric, so it's going to be our fluorine. So hydrofluoric acid is HF plus rubidium hydroxide. Rubidium hydroxide. Well, if we check our periodic table, we will find rubidium here. So it has a +1 charge. It's alkali metal. And hydroxide has a -1 charge, so that is correct formula for that. And this is going to give us, here's my hydrogen, here's my OH, so I've got to have my water, so there's the water, plus, now let's make the salt, the cation from this, and the anion from this. So, rubidium fluoride. And since everything was 1-to-1 all the way through, that is a balanced equation. 1 hydrogen, 1 hydrogen, 1 fluorine, 1 fluorine, 1 rubidium, 1 rubidium, 1 OH, 1 OH. And this is exactly why I leave OH written like this when I'm doing neutralization reactions, just so that we see it's just easier. Hydroxide, hydroxide, hydrogen, hydrogen. It just makes it simple, but we all know that that is water, H2O. All right, calcium hydroxide and nitric acid. So, calcium hydroxide, well, calcium has a +2, hydroxide has a -1, so we have to make that formula this way, plus nitric acid. Well, nitric acid, if you remember, nitric acid, since I don't have hydro in front, it is an oxyacid. So I have to look on the back of my periodic table, nitric, so 8-ic-I-us, 8, so that would be nitrate. So that would be HNO3 yields, now put it in my water, HOH, so that would be the H and the OH here, and cation from the base, anion from the acid, so calcium nitrate, calcium nitrate. Now let's check our balance. I have 1 calcium here, 1 calcium here, that's fine. I have 2 OHs, but only 1 OH over here, so that means I'm probably going to need to put a 2 here. Now I have 2 of the H's, but I've got 2 nitrates over here, and I've only got 1 hydrogen and 1 nitrate over here, so if I put a 2 here, we're all in balance. 2 more to go. Hydroselenic acid. Hydroselenic acid, I know it's binary because of the fact that it's hydroselenic acid. And let's see if I can figure what selenium is here. That means it has a -2 oxidation. So that means that would be H2Se plus aluminum hydroxide. Aluminum hydroxide. We know that aluminum has a +3, hydroxide has -1, so it's going to take 3 of those. And that produces, well, let's do our double displacement. I know that 1 is going to be my HOH, and then aluminum selenide. Well, aluminum is +3, selenide is -2, so after doing my crisscross, and so there's my skeletal equation, but we can look at this and tell straight away this is not in balance. So let's just take a look across the board here. I'm going to leave the water for last. I've got 2 aluminums here, so that means I'm going to need 2 aluminums over here. I have 3 seleniums here, which I've only got 1 on this side, so I'm going to put a 3 here. Well, now let's take a look. Did that get us all straightened out? 3 times 2 is 6. Uh-oh. So no, I don't have it yet. Okay, so what I'm going to need to do is put a 3 here. Alright, after we take a look at this, what we find is that I don't have enough hydrogens on this side, because you can see there are 6 here, so this needs to be 6. And now we should have be in balance. 6 hydrogens, 6 hydrogens. 6 hydroxides, it's 6 hydroxides, 2 aluminums, 2 aluminums, 3 seleniums, 3 seleniums, and there we go. Alright, finishing it up with what should be an easy one. Potassium hydroxide plus chloric acid. So what would chloric? Chlorate. So I've got to have chlorate. Chlorate has a -1 charge, so I only have 1 hydrogen, so there's chloric acid. Now let's see if we can figure out what everything is. Of course, I've got my water, and then my cation and my anion, so plus potassium chlorate. Well, chlorate is still -1, potassium is +1, so there you go. That's correct. That's right. Now since everything was 1-to-1, that should be in balance. And there you go, and really we should all remember everything that was going on with acids and bases anyway, because we just reviewed that. So that's everything for your performance exam, which will be on Thursday the 16th of this week. Well, Thursday the 16th, which is this week. Alright, be sure to ask questions if you need clarification.